these are the answers to the Electrochem test we had a couple days ago. In the first question it asks, what are the oxidation numbers to all the atoms in each of the following? So the rules usually are that when an element is an ion, its oxidation state is the same as the charge on the ion. If an atom is trapped within a polyatomic ion, we assign some typical oxidation states. So typically oxygen is a -2, except if it's in peroxide, in which case it's -1. So in nitric acid, oxygen is 3 times -2. So we have a -6 attributable to the oxygen in nitric acid. But the nitrate anion is -1. So something is bringing it up to +5. And that has to be the nitrogen atom. So nitrogen is +5. Hydrogen is +1. So we're going to write +1 as well because it's the same as its charge. For cupric chloride, the chlorine is a halogen. All the halogens are typically -1 when they're in the ion state. When they're, for example, in aqueous solution, chlorine, fluorine, bromine, iodine, they're all going to be -1. There are 2 chlorines, so 2 times -1 gives you -2. Something has to be +2, and that's the cupric ion. Finally, in magnesium sulfate, we have oxygen 4 times, so it's going to be -8, but the sulfate anion is -2 overall, so that means the sulfur has to be +6, and lastly, magnesium is +2. In the second question, we're asked to balance the following. We show chromium reacting with nitrate anion to give you chromic, and nitrogen monoxide under acidic conditions. So the first thing is to isolate the half reactions. The chromium and the chromic are one reaction, and the nitrate and the nitrogen monoxide are the other. We always balance the half reactions following a recipe where we begin with oxygen, then hydrogen, and finally the charges using electrons. So the oxygen is balanced using water. You see that there's no oxygens in this half reaction, so the only thing we have to worry about is the charges. Chromium is becoming chromic, so we need 3 electrons to balance the charges here. There's no charge on this side of the half reaction. This side of the half reaction will be balanced with a 3+, will be balanced with a 3-. With nitrate turning into nitrogen monoxide, there's a deficit of 2 oxygens, so we're going to make that up by adding 2 water molecules. The 2 water molecules introduce 4 hydrogens, so we're going to balance that off by putting 4 H pluses. And then we'll notice here that there's no charge on this side, but this side has 4 hydrogens and 1 negative in the form of nitrate. So we're going to balance that off to 0 by adding 3 electrons. The 3 electrons of the 2 half reactions cancel, and we add 2 half reactions below, adding also the phase of each one of the reagents. So nitrate is aqueous, hydrogen is aqueous, chromium is a solid, nitrogen monoxide is a gas, 2H2O liquid, and finally chromic ion. In 2B, we're asked to balance this equation, phosphite reacting with permanganate to give you phosphate and manganese dioxide under basic conditions. So when we're asked to balance under basic conditions, we find the answer first under acidic conditions, and then we just add an extra step to the regular way of doing it, where we convert the H pluses into water by adding hydroxide, and then it will balance the equation under basic conditions. So the first step here is to find the half reactions. Phosphite turning into phosphate, that's what I wrote initially, and permanganate turning into manganese dioxide. So I had these 4 things written down at the beginning. Then to balance phosphite turning into phosphate, we see that there's an extra oxygen being added. So we're going to add H2O, 1 H2O to the phosphite, and that's going to give us the 4 oxygens we're looking for, both left and right. By adding the water, we create an imbalance of 2 hydrogens, so we're going to add 2 H pluses on the right. Now we look at the charges. The phosphite and the phosphate balance. So there's only a surplus of 2 positive charges due to the protons, so we're going to add 2 electrons, and that's going to balance the charges. The permanganate turns into manganese dioxide. We have 2 extra oxygens on this side, so we're going to add 2 waters to the right, and that's going to give us 4 oxygens on the left, 4 oxygens on the right. that creates an imbalance of 4 hydrogens on the right, which we're going to balance off by putting 4 hydrogens on the left. Then we look at the charges. 4 pluses, 1 minus. We have it's like having 3 pluses on this side. There's no charges on that side, so we're going to balance it by adding 3 electrons. Now we notice that the half reaction, the first half reaction has 2 electrons. The second half reaction has 3 electrons. So we're going to balance it algebraically by multiplying the first one by 3 and the second one by 2. We write the result below. So everything in this whole line is multiplied by 3. Everything in this whole line is multiplied by 2. And that allows us to eliminate the electrons, because you'll get 6 electrons on the right, 6 electrons on the left. I write the result over here, and then I proceed to balance it under basic conditions, even though I have the answer for acidic conditions. We see I had 6 H pluses and 8 H pluses. So what we do is first I crossed off the 8 and the 6 to give me 2 H pluses. And then I realize, okay, now we have to balance off the 2 H pluses by adding hydroxide. So I add 2 hydroxides to both sides. This turns the proton with the hydroxide turns into water. Now we have 2 waters, and initially we also balanced the waters, sorry. We had 3 waters and 4 waters. I crossed those off and I had 1 water. So I have 1 water on the right. This turns into 2 waters, but I balance it with this one by crossing them both off and writing 1 water on the left. Okay? And then we write everything. It's going to get a little bit jumbled at this stage, but we rewrite everything neatly. Everything that's been cancelled is left behind, and we write 3 phosphites aqueous plus 2 permanganates aqueous gives you 1 H2O liquid with 3 phosphates aqueous and 2 manganese dioxide solid and 2 hydroxide. That's the final reaction balanced under basic conditions. The third question gave you 2 reactions written as reductions. All right, so the cadmium ion is being reduced to cadmium, and VO2 plus, I forget what this is called, is being turned into VO2 plus. This one has a negative reduction potential, so we know it tends to run the other way. So we're going to flip this reaction. We're going to leave this one as is, but we're going to multiply it by 2. But even though we multiply it by 2, the voltage stays the same. You just have more electrons, but of the same voltage. That's what, when we multiply reactions, we leave the voltage the same. The voltage does not increase. Remember that voltage is a measure of how much energy each electron is carrying. So if you have twice as many electrons, you have more energy, but each electron has the same voltage. Each electron is carrying the same amount of energy. You just have more electrons by multiplying the reaction by any given number. Once we've multiplied them, this is the result. Now we have 2 electrons on the left, 2 electrons on the right, which we can eliminate, and then we write the final result down here. And the standard reduction, the standard voltage for this reaction is 1.403 volts. I like to, when I calculate the voltage of the cell, I like to write one reaction as a reduction and one reaction as an oxidation. And then I know that I simply have to add these 2 quantities. As long as one of them is an oxidation and one of them is a reduction, then all I know is that all I have to do is add those 2 together. And you can't get it wrong. Whether you do the oxidation first or the reduction first, it doesn't matter. Just simply add them together as long as one of them is an oxidation and one of them is a reduction. In other words, the electrons have to appear on opposite sides of the reactions. If you have electrons appearing both on the left or both on the right, you're doing something wrong. You cannot have a chemical reaction, you cannot have a redox reaction where where both things are giving up electrons or both things are taking electrons. Something has to give up the electrons and something else has to take them. Finally, the last question is, which elements make the best reducing agents? Explain why. I wrote alkaline metals such as lithium, sodium, and potassium, each with fairly large negative reduction potentials, are the best reducing agents. The large negative reduction potentials of these metals indicate that they are very good at giving up electrons. So when when the reduction potential is negative, it means the reaction tends to run the other way. So all these metals prefer to undergo oxidation. They prefer to lose the electrons. Other indications that a substance is a good reducing agent is a low ionization potential and a low electronegativity. Both of these quantities are measured at least partly as a function of the atom's attraction for its valence electrons. A low attraction for valence electrons makes it easier for them to lose electrons to another element. All of the above are easily oxidized. So the best elements for reducing other substances undergo oxidation very easily themselves. Incidentally, lithium is probably the best metal for making batteries because it has the added advantage of also being very light. It has the highest oxidation potential, and it's also a very low density metal. So those are two qualities that make lithium the metal of choice for making batteries.